This chute had the living shit kicked out of it. A massive hole in the bottom, rebar sticking through it, and a ton of tile missing. The short, we fixed it with a high performance beaded ceramic epoxy lining in under 6 hours, and now it's seen 8 million tons of coal. We're gonna go over their running conditions, what the problem was, and the window that we had for that repair, what we did to fix that hole, as well as protect the chute long term, and then the results of that repair and where we've gotten in 6 and 12 months. If you're new here, I've spent nearly a decade with these types of repair and protection systems, from $200 quick fixes to $3 million projects. I share this information in the hopes that you can use it in your facility. Without further ado, let's dive in. So what are their running conditions? For this chute, they run between 2,000 and 4,000 tons of coal per hour. For argument's sake, let's just say 3,000 tons per hour. They blew a pretty sizable hole, not just through the steel, but also the ceramic tile itself. So what was the problem with this coal chute? Well, again, they run 3,000 tons of coal through this chute per hour, every hour. Coal causes wear, obviously, but so does unforeseen metal. And when the magnets don't catch it, the chute does. And the metal that wasn't caught by the magnets damaged the tile, and over time chipped all of it out, and then went through the underlying steel. This caused inconsistent operations and plugging in the chute. How small was the window for repairing this coal chute? Well, for starters, I got the call on a Monday and had to be there to do the repair on a Tuesday. Once I got there, the window I had to complete everything was just 12 hours. And if you count the cure time for this type of material, we really only had 8 hours to get the whole thing done so it could cure in time to start back up. How do I prepare the surface for installing this beaded wear compound? When dealing with coal chutes, there can be a ton of left behind coal in the chute itself. So first I start with an initial wash down for safety to make sure that everything from the top of the chute all the way to the bottom is completely clear. From there, I do a more focused wash in the problem areas to get rid of as much debris as possible. After that, chisel and chip out any firm adhered coal and loose tile that may have been busted during their operations. Lastly, grind the surface for any further adhered coal and to give us a nice profile to be able to adhere to. So how do you fix a hole like this, especially with the short 8-hour window that we had? Well, with that time frame, we couldn't install any carbon fiber, and we couldn't weld in any new plate because of the tile that's still there. If we do weld, we'll damage the adhesive, causing more tile to fail. So we pre-cut several plates in the field, and we landed on more smaller plates that we could follow the contour of the chute itself, which had a slight curve to it. Then we held them up with fast setting epoxy and self tappers to give us a nice wall that we can do our next steps with. Now our next step was to prime the surface prior to installing our beaded ceramic epoxy. We need to help that beaded ceramic adhere to both the underlying steel that makes up the chute as well as the surrounding tile that hasn't yet been damaged. With heavier build systems like a beaded ceramic, I always recommend using a primer to help them adhere better and get the most performance out of that repair system. They might stick just fine without a primer, but they'll stick even better with a primer. Why do I think beaded wear compounds need a primer? Well, a key point with wear compounds, especially the beaded type, is that they have generally poor adhesion compared to most epoxies. This is because a beaded wear compound is often thicker and even grittier than a more common epoxy, where you can think of it like paint. And because they're grittier and have more functional additives to them, they don't have a lot of good contact area with the substrate. This is why, to help with this, I always recommend a primer, and I like to use a thicker, it's still thin but thicker, direct to metal material. And often a thin film ceramic is a good direct to metal lining with outstanding adhesion. And often you can build these pretty thick. They're brushable but almost squeegee grade, which means you can put down a lot of material, which means once that material begins to set and you apply that beaded wear compound, you can in essence mash that beaded wear compound into the now starting to set epoxy primer. Think like pushing rocks into mud. So now you have great adhesion from the steel to the primer, and because you smashed that beaded wear compound into the primer itself, you have great adhesion from the primer to the beaded wear compound, which means you have excellent adhesion from the steel all the way to the top of the beaded wear compound. Now, to rebuild in heavy wear environments, we're using, you guessed it, a beaded wear compound. More specifically, a beaded ceramic epoxy lining. And so this is a wear compound with beaded ceramic in the epoxy itself. Now this material can build an inch thick to match the existing tile in this particular chute, and it can fill in gaps where the steel plates overlap the hole that we already fixed. An important general note for you when you're working with ceramic wear materials for heavy wear environments, all else being equal, let's say you put down a 1/4 inch of wear compound. If that 1/4 inch gets you, let's say, a year, then if we put down an inch, we're going to get 4 years. And wear compounds are pretty linear in that respect. So why do I use the beaded wear compound that I use? Well, first, beaded wear compounds themselves are great across the board for wear resistance. And we're dealing with 3,000 tons of coal per hour hitting this spot. And this particular material that I use has ceramic beads, has ceramic powder, has ceramic fiber, and has Kevlar fiber in it. Each of these getting successively smaller to help protect the weakest point of the whole system, which is the resin itself. Compared to the ceramic, the resin is the weakest part. So for wear resistance, we want as much ceramic as possible with as little resin as possible. Just enough resin to hold the system on the steel and together and not a drop more. What's a good pecking order for ceramic reinforced epoxies? Bird feathers? Get it? Pecking order? God, I'm stupid. Just kidding. First up, we have non-ceramic reinforced epoxies. And epoxies themselves are actually pretty good at resisting wear just in general. They're very strong resin, but not anything compared to a ceramic. Sitting above a non-ceramic reinforced epoxy would be a thin film ceramic, and this is what you would use in tight tolerance applications. Think a pump impeller, a pump internal lining, somewhere where we need some ceramic but we don't have a lot of room to work with. That's where you'd use a thin film ceramic. Moving above that would be a thick film or a paste grade ceramic, and this is something that you can use in all the same spots as a thin film, but generally you're doing this where you don't have as much of a tolerance concern, or if you have heavy wear or heavy scoring where you need to build back 1/8 of an inch, 1/4 inch, maybe even 1/2 inch, this is where a thick film or a paste grade ceramic works exceptionally well. Now for a resin-based system, the best of the best here would be a beaded wear compound, and this is because of the sheer volume of ceramic in that particular resin system. And so where a thin film system might have 15, 20, 25% ceramic, and you move up a little bit for your thick film systems, beaded wear compounds can have 60, 70, 75% ceramic by volume, which means you have a lot more ceramic content in there, and all of our wear resistance comes from the ceramic. So more ceramic equals more wear resistant. Now, the best of the best here, even above the beaded wear compound, would be ceramic tile. And in the same way that the beaded wear compound has more ceramic than everything beneath it, ceramic tile is quite literally all ceramic. Now, you could argue might be 95%, maybe 97%, maybe 98%, but regardless, it's even more than the beaded wear compound, and it's one continuous piece of ceramic. And so for that reason, it is the best of the best, and you can adhere it with an epoxy with different resins depending on what you're trying to do. An important note though with the ceramic tile is that these have more issues with complex geometries, where your wear compounds and your thick film paste and your thin film paints in essence can go around all sorts of different shapes, geometries, contours, whatever you're dealing with. Tiles are much more difficult to work with in that regard. Doesn't mean it can't be done, but they are more difficult to work with in that regard. However, if you can use them, they are the best, and I'd highly recommend it. Nick, how soon can I put a beaded wear compound back in service? I need to get this thing up and running. So for this coal chute, we completed everything in just under 6 hours. And for this particular beaded wear compound, from the time we mixed the very last bucket, we can put it back in just 4 hours. Now that's at 70 degrees. If it's hotter, we can do it in less time. If it's cooler, it'll take a little bit longer. An important note, this return to service time is very different than if we were going into chemical immersion. For any epoxy system that's going to be going into immersion service for aggressive chemicals, I like to see 120 hours or 5 days of cure. And for mechanical performance, the joke is kind of when it's ready, it's ready. For different resins, that could be 15 minutes or 4 hours or 40 hours. Again, we only had 12 hours to get this done, and with the cure time that we needed, which was 4 hours, we really only had 8 hours to complete everything, and we got it done in 6 hours, netting them about 2 hours across the whole repair. And cure time is different than functional cure, and that's an important point to make. Be careful with the term functional cure, as it may be functional mechanically in 4 hours in a coal chute in the south in the summer, handling 3,000 tons of coal per hour. But if you throw it in sulfuric acid in 4 hours, you're going to have even more problems not long after you return that to service. I talk a lot about a beaded ceramic epoxy that's been reinforced with ceramic. But what do I actually mean by ceramic reinforced epoxy? There's a big difference between a carbon fiber reinforced composite and a reinforced epoxy lining. And it seems tricky or even a play on words to get you to buy something, but there is a reason for it. And I think plenty of people are at least familiar or have heard of a carbon fiber reinforced system. They make phone cases with it, they make cars with it, so it's not a new technology. But then you get to this reinforced lining that doesn't have any carbon fiber in it, and you think, what the hell is this? It just sounds like a bunch of shit. We use the term reinforced to signal that the epoxy lining has been modified for a particular purpose. So a ceramic reinforced epoxy has been modified with ceramic for abrasion resistance. A glass flake reinforced epoxy has been modified with glass flake for additional chemical resistance. A Kevlar reinforced epoxy has been modified with Kevlar to add impact resistance. So this particular beaded ceramic wear compound has been reinforced with ceramic for abrasion resistance and with Kevlar for impact resistance, all in one. You get the idea. Reinforced is a signal word to let us know that that epoxy has been modified for a very specific reason, whether it be wear resistance, chemical resistance, or impact resistance, or the many other resistances that we may want. Is there a wear-in period for a beaded ceramic lining? The short answer, yes. Depending on your media going through that chute, that hopper, that airline, whatever it may be, the beaded wear compound may almost be sticky because it's not smooth, and this can cause buildup due to the imperfect surface finish. Now this is usually caused by the sheer amount of material that's in a beaded wear compound. You got beads, you got powders, you got fibers, you got a lot of different materials in there and a lot of it itself. So you have not just one additive, but often 3, 4, 5 additives, and you have a lot of those additives. So it's a grittier material that doesn't always finish smooth the way we think of car paint or house paint where it's a nice smooth finish. That doesn't always happen. Now for a lot of the coal chutes that I work in, a lot of their wear-in periods are about a week, to where it will almost appear to get worse, where you will have some buildup, and then once that wear compound wears smooth, you're back to normal operations and often even better operations than you had before the repair. Now their original goal was to get this thing just a couple of months, and then from there reevaluate next steps. At the 6-month mark, there was almost no visible loss of material for the beaded wear compound, and it had already seen 4 million tons of coal. So they said, let's just keep the chute running and we'll deal with it in another 6 months. Now, as we near the 12-month mark, that chute has seen almost 8 million tons of coal, and the beaded wear compound remaining is estimated at about 90%. So now I'd say we're well on our way to probably 20 million tons of coal, conservatively, with 30 million tons of coal and beyond very likely. That would take us to 4 years of runtime and counting, and remember, they only wanted a couple months. How can you use a beaded wear compound in your facility? If you're dealing with coal, you can use it on transfers, on chutes, on head hoppers, on conveyor headers, flop gates, and diverter plates. If you're working in pulp and paper, you can use it on bark bins, bark chutes, bark hoppers, bark elbows, slurry lines, and blow line. If you're handling material transfer and conveyance in general, you can use it on chutes, hoppers, diverter plates, slurry pumps and air-assisted material lines, rake systems, and high solids pumps.